All right, hello everyone. The goal for today, if you look at the assignment in the textbook, it says 3.2 complex numbers. We need to do a little bit of pre-work before we get to complex numbers. So that's my plan to start. We're going to talk about something called simplifying radicals. I mentioned at the end of the class period, or the end of when I did my lecture yesterday in class, but we're going to hit it today. So we're going to simplify some radicals, introduce this idea of a complex number, and then do all the operations. We're going to add, subtract, multiply. I'm not going to divide, but add, subtract, and multiply with complex numbers, and then just learn how to manipulate complex numbers a little bit. So that's kind of the plan for today. So by the end of the day, you should be able to work with complex numbers in a variety of formats. That's kind of the objective for today. So let's get rolling. So if you have your some notes, grab your blank piece of paper, and let's get rolling. So first thing let's do is let's talk about this idea of simplifying radicals. Not sure if you've seen it in the past. I know we've done it in Algebra 1, but it's been a while. So let's go ahead and just kind of talk about what it means to simplify a radical, or to put something in simplified radical form. So let's just list a bunch of perfect squares, because we need to know those first. I know some people are going to do this differently. If you go to Mr. Fry's, I think he does prime factorization, but I do it a little different, and which is okay. So this is what I do. So my first step is I'm just going to list a bunch of x values. X equals 1, 2, 3, 4, and so on. We'll go up to like 12. And now I'm going to list all those numbers times themselves. So all those numbers squared. So 1 squared is 1, 2 squared is 4, and so on. You should have the numbers on the right memorized as perfect squares, or at least be able to find them very quickly. And all I'm doing is just squaring 1 through 12. Okay? You won't use 121 or 144 very often, but you should at least know kind of what they are. 144 I think you know, but 121 you may not have known. Okay, simplifying a radical. My first question is this a perfect square? Meaning, if you took the square root of this number, 72, will you get a nice, neat whole number? So I look over here at my chart, and no. 72 is somewhere between 64 and 81, so the perfect, or the square root is somewhere between 8 and 9. It's not a perfect square. So, second question. Is there a perfect square that evenly divides into 72? And so what I would do is, you want the biggest. So I'm going to start up here at the biggest number it could possibly be. Does 64 evenly divide into 72? Well, no. Does 49? No. Does 36? Yes. So I'm going to change 72 into 36 times 2. Notice I left the radical, I left the square root symbol, and I simply multiplied 36 times whatever it needed to be. So I divided 72 by 36, and I got 2. So I can change the square root of 72 into the square root of 36 and the square root of 2. Why would I do that? Because I know one of these. The square root of 36, looking at my chart, the square root of 36 is 6, because 6 times 6 is 36. The square root of 2 is not a nice, neat whole number, so I leave it alone. And I have simplified the radical, or what's underneath the radical, as far as I can. Let's try another one. Square root of 50. Take a second. What perfect square goes into 50? 25. 25 times what gives me 50? 2. What is the square root of 25? 5. And what is the square root of 2? I don't know. Some decimal. And I'm done. Okay? Most common mistake is to leave this 5 still in the radical. It's not. I used the radical to evaluate the square root of 25. And the square root of 25 is just plain old 5. No radical, no square root, it's gone. Okay. Square root of 48. Which one of these goes into 48? I'd start up here and just work your way down. Which ones of these goes into 48? Okay, I can change 48 into 16 times 3. Square root of 16 I know is 4. Square root of 3 is some decimal. Okay, hopefully you got the idea. Ask yourself what perfect square goes into the number, split it into that number and whatever it needs to be to get your number, and you got it. Okay, we're going to keep doing some of these, but I'm going to introduce a new concept. Okay, so what if I wanted to find the square root of a negative 9? Well, I know the square root of a positive 9 is 3, but what's the square root of a negative 9? Well, if we ask myself the question, what number times itself gives me a negative? Answer, nothing. Because a negative times a negative is a positive, and a positive times a positive is a positive. So this does not have an answer. So typically, or not typically, the one answer would be this has no real solution. Well, a while back, meaning a long time ago, mathematicians came up with, we want a way of handling that negative number. So this really is a definition. So they defined I to be the square root of negative 1. You might ask, well, why is I the square root of negative 1? By definition. There's no formula that we figured out. There's no way of calculating it. That is a definition. I is defined to be the square root of negative 1. So, doing what we just did up here, I'm going to simplify this radical by changing this into the square root of a negative 1 times the square root of 9. Okay, just like we did here. I can break that down into the square root of negative 1 times the square root of 9. Well, the square root of negative 1 is just I. The square root of 9 is 3, and typically you write it with the whole number or the constant first, so it'll be 3i. What is the square root of a negative 25? Well, same idea. Square root of negative 1 times the square root of 25. Square root of negative 1 is I. Square root of 25 is 5. And so my answer is 5i. What is the square root of a negative 27? Maybe hit pause on the video and give it a try. Okay, I'm going to split this up into the square root of negative 1. Now, 27. These were perfect, these were perfect squares. This is not. So I go back to what we did in the top part. What perfect square goes into 27? 25 doesn't, 16 doesn't, but 9 does. So I'm going to change 27 into 9 times 3. Square root of 9, I know, is equal to 3. Square root of negative 1 is I. And so this becomes 3i square root of 3. I know this is I. I know this is 3. I don't know this. It's some decimal. I leave it alone. That becomes 3. That becomes I. They are both outside of the radicals. We used the radical to take the square roots. The square root of 3 I don't know. I never use the radical. It stays inside. One more. We'll call it good. Hit pause on the video. Give it a try. When you're done, hit play again. All right. So, negative. I can break that as a negative 1 out. The perfect square that goes into 200 would be 100, and 100 times 2 is 200. Square root of negative 1 is I, square root of 100 is 10, so this is 10i. If you wrote I10, that's correct also. Square root of 2 is just the square root of 2. Okay, so the first concept for today is how do we just simplify radicals And what is this thing called I? All right, step 2. We're going to add and subtract complex numbers. So before we do that, let's define this thing called a complex number. So a complex number has a real part and an imaginary part. And it's technically written A plus or minus BI. A is my real part, and BI is my imaginary part. I'm going to go ahead and do something now that I was going to do later. I can graph this thing on what's called a complex plane. So this down here on the x-axis is my real part, and this up here is my imaginary part. So if I had the number 3 plus 4i, my real part is a positive 3, my imaginary part is a positive 4. So my real part is 1, 2, 3, the imaginary part is 1, 2, 3, 4. So this is the point right there. 3 on the real axis, 4 on the imaginary axis. In electrical fields, if you're going into electrical engineering or any kind of thing that deals with electrical circuits and that kind of stuff, you're going to graph on a real imaginary plane. How about this? -2 plus I. Real part, -2. Imaginary part, +1. So my real part, -2. Imaginary part, +1. Get the idea? How would I graph 4? Well, I just go over here to 4 on the real part. There is technically a +0i out here, so I just plot that point. How about -3i? Well, now my real part is 0, and I just go down to -3 on the imaginary side. Okay? So, a complex number is not just an imaginary number. It's not just the imaginary part. It's not just the I. A complex number is both real and imaginary. So if you are looking at, we'll do a little number theory. If you're looking at set of all numbers, your complex number is everything. Inside the complex numbers, inside the complex numbers is all your real parts, all your real numbers, and all your irrationals and so on. Complex numbers include both real and imaginary numbers. Okay. Yeah, let's just keep cruising down. So we're going to add imaginary numbers together, or complex numbers together. So I have 3 plus 2i, there's one number, plus -4 plus 6i. So if you think about these as variables, the I is just like an X. To add like terms, I can add the real parts together. 3 plus a -4 is a -1. And I can add the imaginary parts together. 2 plus 6 is 8. All right. Combine like terms. Here's what I would highly encourage you to do until you've done these a bunch. This +1 in front of here, when I distribute that, it does nothing to this expression. So I just combine my like terms. Not true over here. This -1 over here changes that +6 into a -6. It changes that -3i into a +3i. So until you get comfortable switching those, or even afterwards, I would always just switch those and rewrite it. Don't just try to do it in your head. Now I'm simply going to combine like terms. +4, -6 is a -2. -2, +3 is a +1i. To combine like, or to add complex numbers, you are simply combining the like terms, just like you do when it's an X. Okay, how about multiplication? How do you multiply complex numbers? Well, kind of just like it is when it's an x. So 3 plus 2i times 4 minus 5i. We're going to FOIL just like we did yesterday. So 3 times 4 is 12. 3 times a negative 5 is a negative 15i. 2i times 4 is positive 8i. Positive 2 times a negative 5 is a negative 10. And I times I is I squared. Okay, what is this I squared thing? Well, if I is defined to be the square root of negative 1, then I squared is the square root of a negative 1 squared. Right? That's what squared means. So it's the square root of negative 1 squared. Well, a square just simply cancels the square root, and so I squared is a negative 1. Okay? So when I multiply complex numbers, I do it just like I did back in yesterday when we did it on the board, but whenever I see an I squared, I replace it with a negative 1. And so this becomes a negative 10 times a negative 1, which is a positive 10, and 12 plus 10 is 22. My like terms here gives me a negative 7i. So these multiplied together gives me that complex number. You cannot have an I squared in a complex number, because notice what the definition of a complex number is. It's a plus or minus something times I. There is no I squared. There is no I cubed. This is a complex number. So when you are done adding, subtracting, multiplying, dividing, whatever, your answer has to be in complex number form. Now, you may have a 0 here. That's okay. You may have a 0 here. That's okay. You just can't have a squared, a cubed, or whatever. Okay, your turn. Multiply that together. Combine your like terms. Hit pause. Give it a try. Okay, first step. 2 times 3 is 6. 6 times 2 is 12. Negative 5 times 3 is negative 15. Negative 5 times a positive 6 is a negative 30i squared. I squared is negative 1, so this becomes a positive 30. Combine my like terms, I get 36. 12 minus 15 is a negative 3i. And I have my real and imaginary part. All right, there is multiplying complex numbers. All right, next thing. There's something called a complex conjugate. So a complex conjugate is simply the same expression as you had before. So if I have, not A, don't want A. What if I have 7 plus 6i? The complex conjugate changes the sign of the imaginary part. So the complex conjugate for this is 7 minus 6i. Okay, by definition. Complex conjugate, switch the sign of the imaginary part. So if I have a negative 4 minus 3i, the conjugate would be a negative 4 plus 3i. Notice the only thing that changed is the imaginary part of the complex number. Real part stayed the same. Real part stayed the same. Okay, why would we need a conjugate? What's so special about a conjugate? Let's multiply a number times its conjugate and see what happens. So I multiply 7 times 7 is 49. 7 times a negative 6 is a negative 42. Positive 6 times 7 is a positive 42. And a positive 6 times a negative 6 is a negative 36i squared. Give you a second to catch up. I squared is a negative 1, so just like before, that becomes 36. Get these out of the way. And so I end up with 49 plus 36 is what, 85? Negative 42, positive 42 goes away. So what did the conjugate do? It changed it got rid of the imaginary part. Okay? That is always the case. So we're going to use this in order to divide, but that's not today. Okay, so my conjugate, what does it do? It changes a complex number that has both a real and an imaginary part to a complex number that just has a real part. Okay, your turn. Try the bottom. Multiply those two conjugates together and see what you get. Hit pause and then come back. Okay, multiply the negative 4 times the negative 4, I get 16. Negative 4 times the positive 3 is a negative 12i. This becomes a positive 12i. This becomes a negative 9i squared. These two go away. This becomes positive 9, and my answer is 25. When you multiply two conjugates together, the imaginary part goes away. Okay, last topic. So what is all this for? There are times when you will get down to an answer of a quadratic, of a squared function that's negative. So how do we handle that? Well, just like before, in order to solve this, in order to get the x by itself, I have to take the square root of both sides. And when I square root a variable, or square root a square when there is a variable, I get both the plus and the minus. Square root of x squared is x. This becomes plus or minus. Remember how we did that earlier. This becomes the square root of a negative 1 and the square root of 9. Square root of negative 1 is I. Square root of 9 is 3. So my answer is plus or minus 3i. How does that work? Let's just double check. If I took 3i and square it, I should get a negative 9. If this is a solution to my original problem, remember my original problem? When will x squared equal a negative 9? Typically we say never. A squared can't be negative. Well, let's be more precise. When we say never, what we really mean is there's no real number that makes that work. But there is a complex number that makes it work. So let's double check. Is 3i squared a negative 9? This squared goes to both of these terms. So 3 squared is 9. I squared is I squared. And I squared is a negative 1. So this really is a negative 9. It works. Okay, so why are we using complex numbers? To solve quadratics and allow us to deal with complex solutions. Let me give you one. X squared plus 25 equals 0. And while you're at it, we'll do another one. 3x squared plus 10 equals negative 14. Hit pause, try both of those. When you're ready for both of those, come back. Okay, hopefully you're back by now. First step, remember yesterday we talked about how to solve something that has just a single x squared. I want to isolate that squared term, so I need to subtract 25 from both sides. X squared term is isolated, so I need to take the square root to get rid of the square. And the square root of a negative 25, remember, was the square root of negative 1 and the square root of 25. This is 5. so this becomes 5i. And we get the plus and the minus because when we square root a square, we get both the plus and the minus. Okay, next question, same thought process. I want to isolate the x squared. I want it to be x squared equals something. So first step, undo what's being added or subtracted. Subtract 10 from both sides, divide by 3, take the square root, and I generate plus and minus. Break the negative 1, or the 8 in, sorry, break the negative 8 into negative 1 times 4 times 2. Why did I pick the 4? Because 4 is a perfect square. Remember back at the beginning of the video. Okay, square root of 4 is 2. Square root of negative 1 is I, so this is 2i. Square root of 2 is just square root of 2, and the plus or minus. One more. So the questions on the homework are going to say, find the roots of the equation or the zeros of the functions. Same thing. Okay, so don't let the terminology root and zero confuse you. You're finding the exact same thing. A root of an equation is when the equation equals a 0. A zero of a function is when the function equals 0. Why do they have two different names? I don't know. Blame those math people. All right. Find the zero of this function. What does that mean? What value for x will make the function equal 0? So put 0 right here and solve. Remember what we said yesterday? In order to solve, or in order to factor a quadratic, it has to be equal to 0. So here's my quadratic, and we're going to set it equal to 0. But in this case, the only reason why we're setting it equal to 0 because it asks me to find the zeros. Okay, hit pause, solve that, come back. Okay, I went ahead and did it while we were on pause. So first step, I want to isolate this x squared term. Okay, so this x squared term needs isolated, so I'm going to add 24 to both sides. Divide by negative half. 24 divided by half is 48. Square root both sides, I get the plus and the minus. Square root of negative 1, square root of 16, square root of 3. Why did I pick 16? Because it's a perfect square. Evaluate the ones I know. Square root of negative 1 is I. Square root of 16 is 4. Square root of 3, I don't know. It's a decimal. Leave it alone. You're done. Okay, that is today's topic. This will be on the board also, but here is your homework, maybe, if I can find it. Here is also your homework. We're on page 105, numbers 11, 17, 19, 31, 43, 57, 63, and 73. And these just walk you through the same type of questions as we just did on the recording. Okay, hope that helped, and see you when I get back.